So hello everyone, so welcome to our this week Rogers Efficiency Seminar. And today we're very glad to have Dr. Liangliang Cao from the Google AI to give us this talk. Dr. Cao is currently a senior staff research scientist at Google, and he has acted as the tech lead of the Google Cloud Speech and Google Cloud Vision modeling. And he was a recipient of the ACMC MMM Rising Star Award and has published more than 100 papers in top conference and journals. Before joining Google, he co-founded the Sweetie company and worked as a CTO. And this company was acquired by Google, right? And he also worked in the IBM Watson Research Center and the Yahoo Labs. He enjoyed teaching and had taught several classes at the Columbia University from the 2013 to 2018 as an adjunct associate professor. And now let's welcome Dr. Cao to give us this talk, reducing long-form errors in end-to-end speech recognition.
Thanks, Professor Yan. Can people see my screen?
Yeah, I can see your screen. Yeah.
Oh, thank you. So I cannot see my screen. So feel free to raise a hand if you see any problem on my talk or if you have any questions. Feel free to interrupt me. So today I'm going to talk about the work we have done in the past 2 years in Google. That's a collaboration with many Google colleagues. So you see a lot of numbers, a lot of names here because we kind of share the code base in Google between researchers and the production code base. So among them, 3 papers I mentioned today are first authored by T-Bot and Zhiyun in my team. And we also have close collaboration with many fantastic colleagues in Google Speech, Google Brain, Google Research, etc., and Google Cloud. So I'm going to talk about mainly grouped into 4 topics. First, I will give a background introduction about what is end-to-end speech recognition. Then we'll talk about the topic we want to discuss today. It's called a long-form error. And then we will show some interesting study. We call that universal perturbance, universal adverse attack. And then we have some method to improve or solve this problem. The first step is a teacher distillation. Another is how to improve the teacher, like we combine the CTC and RNT. I will explain what is CTC and RNT in a minute. I know it's kind of little bit heavy, condensed all the content in this, especially end-to-end speech recognition itself is a big topic. So I will try to explain kind of as fast as I could, and I will share the slides just in case you have any questions, like you can read the slides offline. So what is end-to-end speech recognition? ASR is acoustic speech recognition. And I borrow my colleague Bo's slides. This is a very nice tutorial. So conventionally, traditionally, we call that the speech recognition several years ago called that conventional speech recognition. So a big picture is we give the input speech, we extract feature, and then send it to some we call acoustic model. A typical acoustic model can be deep neural network or recurrent network. You can think the Hinton has a very Jeffrey Hinton has a very famous paper, like many famous co-authors, like changing the DNN in speech recognition, probably around 2011, so 2012. Hinton's speech recognition paper, probably the first deep learning paper, even earlier than computer vision AlexNet, because deep learning was the first have found the success in speech recognition. But even that was still conventional in today's perspective or standard, because it used the acoustic model and it requires a separate module. We call that the language model. So the language model, this is the acoustic model. After acoustic model, it generates speech generate text. And then we have a second pass scoring. This is the decoder part. It's called a language model. Basically, usually we collect a lot of text data offline, compute their prior, like called language modeling, and which think that n-gram, bigram, or trigram, and then use this to adjust the text generated from acoustic model. There are a lot of modules between the two. For example, acoustic model learning, we have trained, we already have a GMM model. We have some alignment, the speech phonemes together with the speech signal, and then combine them together to generate not tokens. And token will be sent to the language model. Do first pass decoder, and then we have clustering, pronunciation lexicon, and first pass AM, second pass language model. It's usually a very complicated system. As a result, even in big companies, to train conventional speech recognition may take several weeks or even months to train one and refresh the model in production. Things happens, the change happened, I think, 4 years ago. People are looking for end-to-end learning paradigm. End-to-end learning is we don't separate acoustic learning and acoustic speech recognition and the language modeling part. Instead, we want to combine them together. By combining, that means we want to optimize some metric directly. Typically, in speech recognition, we minimize optimize the word error rate. To understand what's end-to-end learning, we can think as, for example, AlexNet. For computer vision, AlexNet is end-to-end method, but the dense shift-based approach was not end-to-end learning because it just has many steps. You need a clustering, you need to do offline finding the centers, and then you do encode. You need to map each image into long vector and so on and so forth. So if you have multiple stage and different stage have different object function, then that's not end-to-end. And recently, I think in computer vision, the DETR is the end-to-end object detection, but the faster RCN is not end-to-end because you have another different steps, like for example, the non-maximum suppression is make the module not end-to-end. So end-to-end learning has some advantage that we just directly optimize the metric. That means we probably have more room to reduce the word error rate or improve the accuracy. And we will heavily rely on the accelerator. That means TPU or GPU, those accelerators will do the heavy lifting job. And to give even a bigger picture, so in conventional speech system, we have many modules. Acoustic model, pronunciation model, language model, or verbalizer and pointer. And in end-to-end learning, we just have one. If we compare with two, the first one is end-to-end learning can be learned, can be trained with a very simplified pipeline. So because the pipeline is simplified, so the learning training process can be speed up. Previously, we need to wait for several weeks, but now usually we wait only 3 days at most. For liberal speech, maybe 1 day. For even bigger scale, at most 7 days. So the training is much easier, faster, but at a cost, we need a lot of GPU. Sorry. Any question? Okay.
Is there any question?
Okay. I will keep talking and feel free to raise your hand or interrupt me. The most important thing, also, sorry, end-to-end learning usually is good with large scale training data. That's some well accepted, but not many people explicitly say so, because if you want to do end-to-end learning, if you only learn on small amount of data, you're really easy to get to the suffer from the fact that the model do not generalize well. But if you learn from large scale training data, end-to-end learning first can optimize the criteria, the metrics directly. Second, it can utilize the power to expand. Hopefully, the training model will have better generalization ability. The last one, in fact, is the most important one. So changing from conventional speech to end-to-end learning is a big change from the production point of view. So we need to find a niche area that clearly shows that end-to-end learning can win. Otherwise, if you say, oh, I want to change a working system with a new system without explicit or the very convincing argument that the new model can win, then you will get pushed back by the production system. We have seen a lot of such cases, not only in Google, but in general in speech industry. In fact, the last benefit become the reason that end-to-end model was first launched, because end-to-end model is much smaller than the conventional speech recognition system. The major issue is because in conventional system, the larger model is very big, because he need to use a lot of unigram, bigram, trigrams. So larger model can be much bigger, but if we learn them together, the end-to-end model is more compact. It's usually 10 times smaller than the conventional model. So that's motivate the end-to-end model first launch in production. In production means first launch on device, like your phones or some on-device speech recognition, and then later, little by little, we replace the conventional model in different production system and try to see how to make them better. There are several different end-to-end ASR models. And in Google these days, most of the time we use RNT, called RN Transducer. It follows the paradigm like encoder, which is the RN, and the decoder, which is transducer. But I list the CTC and the LAS here because in our research, later we'll show that although CTC and LARS are not used in production, they will be very helpful, especially for CTC, will be very helpful to train as a teacher. So we launch a student model in the production, but the teacher, we will use multiple, both CTC and RNT as a teacher. And recently there's new generation of RNT, we call that transformer model or conformer model. Conformer means convolution plus transformation, transformer. They can be viewed as a special case RNT. So in the next maybe 5 minutes or 10 minutes, I will go through this model very quickly. So the CTC model is, suppose we have encoder, every sequential XI, XT is the speech feature, usually the frequency domain, a long vector for at each step. And then we see these the speech feature and send them into encoder. Encoder get the hidden encoder feature and send to softmax. And then we have the YI plus YT, all kinds of, every token has a probability. So the biggest, at least the paper, I think Alex, who was a Hinton's postdoc, was published the CTC model early in 2014. And then the Baidu the team led by Andrew Yin published called Deep Speech 1, Deep Speech 2 in 2015. The benefit of CTC is it does not require the frame level alignment. So previously in conventional model, we need say, oh, this is a speech signal. At each speech signal, we need to align the ground truth of the text, the transcribed text with the speech signal. That means every token need a map to a certain frame so that we can do the learning. But CTC does not need so. And then CTC will compute the alignment by using the called CTC loss. And how it's done is I just show a simple case. Like suppose there is multiple tokens B, C, A, T, and the CTC will introduce a special symbol called blank, here denoted as B, and maximize the total probability or the label sequence by margining over all the possible alignment. And the one with the highest possibility will be the final alignment generated. And the B just say, oh, this is empty space, empty frame. We don't estimate anything. CTC is a model that mainly using encoder, no decoder introduced. And the second model I'm going to talk about is called LAS, listen, attend, and spell. It is pretty complicated one, but when it was published, it received a lot of attention. It has encoder and also have attention. Attention is more like alignment and also like a decoder. And the paper was published at CASP 2016. At that time, it's called Listen, Attend, Spell. Encoder, attention, decoder. Encoder you can think as analogous to acoustic model. Decoder you can think as longer modeling, and the attention here we just do the alignment. Lars, mathematically, Lars is probably the most beautiful model among all the things we are talking about. But Lars has also his problem, and these days we don't really use Lars too much in the production system. The last one are probably the most important for us now is called recurrent neural network transducer. So also was first proposed by Alex. The changes compare with the CTC. The CTC just do the encoder for every frame, but the RNT will introduce the information from previous frames. Like suppose in CTC we have the output at every frame, but now if we put this previous frame result back to the encoder together with the encoder, probably we will get better information to generate the sequence. So here is become the new model on the right picture on the right. So we have encoder as CTC. We also have the prediction from the last or previous network. We called the YU -1 or YU -2. These YU are the prediction. They are not the ground truth. So from the predictions, we combine the previous prediction and the encoder output into joint network, and then send together become the prediction of the T. And then the YU T will send back to the encoder for next frame prediction again. And here I will just use a few examples to show how the CTC work. So suppose we have some speech signal, it comes in, the first signal will say, oh, first signal will say, oh, this is nothing, just blank, and the softmax will estimate blank. SOS is kind of just a starting signal. So let's go to next frame. Currently frame T plus equals 1, and then we go to next frame will become, oh, still nothing, because a lot of times the frame can be just estimated, not too much estimate. Now there's some speech signal in the third frame, and then what will happen is the encoder will generate a feature, and then the joint network realize, oh, there is something, and then they send it to the final and estimate the token is C. So C is no longer blank, and then C will come to used, it's token here, is just here is the C. C will be used here, and then next frame after C is we get encoder using the predictions from the network G, and then do the joint network and then softmax A. And then we can do this frame again, and at last become output cat. The cat will be the transcription result from the RNT. So after T frames, the inference will terminate when the out input frame has been consumed. So here is the matrix become how the inference will go. So we have ground truth, CAT. We also have the frame from the each t equals 1 to equals 5. And then we have a path. In fact, this path will be how the CTC will learn. So the path will be starting from empty, and then go to find the first token C, and then go to find the second token A, and then find the last token. Some tokens here, the token T, can consume multiple frames. But if you look at the path together, the estimation is clear that is CAT as the prediction results. Implement this on CPU is not on TPU is non-trivial, but fortunately, we have very efficient implementation in Google, and we can do this computation pretty fast. And a lot of libraries these days have been open source to compute this RNT, optimize this RNT loss. So I need to go forward. We haven't talked about any innovation from my team now. But just I leave some links. So this blog explains how the RNT first be launched in Google production. Johan was our VP, speech VP at the time. And also they have a number of papers after 2019, especially last year, explaining how the RNT was used not only on device, but also on server these days. So despite the success of RNT launched in production, there are some problems. So one of these problems, in fact, was published in 2021. So basically this paper was doing is showing that when the number of the vertical length is the horizontal length is the horizontal x was the length of the input, the speech audios, the length of speech audios. Basically, it shows that if the RNT was applied to some audio, noisy audios, the deletion error. So here the blue, the red one shows the deletion error. Deletion error will go up when the testing audio become longer and longer. And the deletion error here, we call that a long form error because it happens a lot, happens more significantly when the audio become big. So, in fact, this was a early study. And at the time, we want to publish this paper, but the field, this paper was rejected several times because the field didn't realize that's a big problem for RNT. Finally, we get published and we studied them deeper. We found that if we take Libre Speech a famous public data set, we concatenate the Libre Speech testing set together. Here is we just concatenate just one testing set, which is the original one, and then we concatenate 3, 5, 10. The longer, the more concatenation we have, the longer second we will have. We will see the WER goes up significantly. At last, the deletion error goes more than 70%, and become dominant in the whole WER. So this was shows that how serious the problem is. But fortunately, our production model is better than Libre Speech. We trained from this, but our production model also have this suffer from long form errors, especially for cloud user scenarios. So this is the problem, and that's the topic we want to, the problem we want to solve. We try to solve in the past 2 years. Any question, feel free to interrupt me. Otherwise, I will go to the solution next. In fact, not solution, go to analysis and then solution. Okay, so one study we did at that time is, since we already see the deletion error becomes so significant, can we manipulate or create some speech signal that can generate those long form deletion error? So a good setting is If we believe deletion error will become dominant, can we generate some called magic speech signal and then concatenate with utterance and then concatenating them together, and then we can fuse the model. Of course, people are familiar with adversarial attack. We see that for every model, we can always find those, usually we can find those signals. But the challenging part is we want to find one speech audio that can be applied to all utterances. We call that universal speech adversarial perturbations. So that universal means just for every model, this magic signal can be used for every many speech audios. So here is the problem statement. Suppose we have ASR defined by parameter theta, and we want to have X, some audio speech signals, and we want to apply perturbance, the delta, and plus this X, we hopefully the prediction Y will become almost empty. That means a lot of deletion errors. So to do this, we treat them as a learning problem. The L is the learning. Basically, we want to, the prediction of X, we want them to be as close to be the Y, Y prime. Here, my prime is empty. Just like want to learn this delta by minimizing the loss between the zero predictions. The loss, we can try cross entropy loss, CTC loss, RNT loss, etc. So how we learn this? We basically took the model trained from Libre speech. Here we use the COTR model, and then we minimize this loss function on all the Libre speech training data, and then we learn the expected Y prime is empty for every audios in Libre speech. Here, the model is not updated, but what we learn is we learn optimize over delta, which is the magic short audios. And note that this one can only be applied for the research model we train on Libre speech. We do not use this for Google production because technically the technical difficulty is in Google production, we have a special front end. We cannot compute the gradient over this front end. So this learning cannot be a trigger, but we just want to use a public data set, a public model to demonstrate the problem. So we use Libre speech and we define some metrics. The Y prime is empty here. We also measure the distortion, trying to make sure the audios, the magic audio is not super loud. It's still kind of small compared if we measure distortion. So this is our training curve. So basically, we add some prepend some for our audios. We require the prediction will be all empty. And the learning rates, so different colors shows the different models, RNT model and the CTC models. So basically shows that, oh, such a universal model can be learned after say 50K steps. And I will show, play the audio, show what the magic audio sounds like. You will probably hear some ghost sound or white noise sound just here. Yeah, that's very small. And then prediction for we just this one was the 4 seconds long. We applied to 2 different audios. This is the first audio.
A cold, lucid indifference reigned in his soul.
Yeah, our model will predict as empty. And then we apply to another module.
He hoped there would be stew for dinner, turnips and carrots and bruised potatoes and fat mutton pieces to be ladled out in thick, peppered, flour-fattened sauce.
yeah, again, here the prediction, the model will be fooled by the magic, the 4-second long, and then the overall prediction is empty again. So we also have we also have other audios I will just skip here. And very interesting phenomenon we found is the deletion error happens more heavily on Lars. Here, the deletion error, attack success rate close to 100 means all deletion errors. So on testing, library speech has two sets, testing clean and testing others. But in both cases, almost all the testing set get empty prediction. RNT close, the success rate close to 50% means half of them were just empty prediction. These and the CTC model, in fact, although it's not used in production because it's still bigger than the RNT, but the CTC model does not suffer from learning the adverse attack. So CTC model is most robust to deletion error, long form deletion error. RNT is second, the Lars is the worst. After we understand the problem, we kind of think we gain some insight by playing with this universal attack. So we think to ourselves, how can we solve them? Of course, a very straightforward thinking is, if we have some very noisy background, then probably this noisy background can let the model understand what the noise might be. And then if we learn from this, probably the model will become more robust. So where can we find a lot of noisy data? The answer we got is YouTube. So we don't have a lot of annotated YouTube data. So that means we can probably learn from YouTube unsupervised YouTube data. Here comes our setting. We call that a teacher distillation. So teacher distillation is the motivation is just as we discussed. We want to go to YouTube and find the worst, the unlabeled data source. And the tricky part is where we can find a teacher. Of course, people can think about the teacher can have many possible ways. There are always even papers saying that the self-learning can be very useful, but in our experiment, the most effective approach is we want to use a non-streaming model as a teacher to train streaming student. So what is a streaming student? So when you talk with for example, your mobile phones, you will say, I'm giving a talk. The mobile phone won't generate, will start to generate text. If you use Google Pixel phone, will start to generate text while you are speaking. So it won't wait until you get the audio finished, will generate. So if the model generates the prediction while you are speaking, that's streaming. If the model has to wait until the speech finished, it's called a non-streaming model. The non-streaming model, you can use bidirectional RNT and then use the information from both the past and the future to generate this. Non-streaming model is not welcome for application like real-time transcription, but we can borrow them here as our teacher. And a second insight we got is come from here. We found that the CTC model have become the most robust. So we use the CTC as part of our teacher model. So that's basically our motivation and how we do this. So we basically get unlabeled YouTube data. We random segment them into a 5 to 15, from 5 to 16, the audio segments. And then we borrow a non-streaming teacher, and then basically use the non-streaming teacher to label these random segments. And in practice, it's very important to use a speckle augment, basically learning from noisy data, and then train a streaming teacher. So this paper was published ICAPS 2021, and with T-Bot and Wei. the title is called Improving Speech Streaming ASR with a non-streaming model distillation on unsupervised data. The result model was launched. In fact, that was our team's first field launch in Google Cloud. I cannot show the performance from internal metrics, but I can show the labor speech. So basically, on labor speech, if we take the streaming model, the error is like this. But if we allow the model to be non-streaming, it's the error rate become much smaller. And if we use this teacher to train a streaming student, you see the streaming student is much better than learning from the streaming directly. What is more exciting is the YouTube data. So YouTube data, we have a testing set we called YouTube. We kind of call it long form YouTube data. And we have two types of training data. One is the unsupervised segments. Another is a weekly aligned user upload transcript. So basically, we have combined the Conf Island and the YouTube segments into the training, and then apply our framework and then train the models. The performance was very exciting. It just basically reduced the WER. If I look at the model trains between the Conf Island and the streaming teacher, reduce about 10%, average from 5% to 10% WER. That's huge because if you think about the word error rate, 5%. In fact, in voice search or kind of pixel, we usually have when we have 1% reduction, performance reduction, that's already significant. Here we have close to 10%. That gives a lot of confidence that this kind of approach works. So what happened is we just spent 1 year, almost another year, just to optimize this approach. And next, I will report one of the final thing, one of the techniques we found very useful. So the key motivation is to do better. We need to look at CTC model and the RNT model because CTC is more robust. So intuition is if we can borrow the CTC model to train RNT, kind of model are different. The teacher and the student are different types of model structure. Then we hope CTC is more robust than the RNT. So what happened is we use 3 different kinds of teacher model. The first 2 characters shows where the data is from. The MD is kind of multi-domain, the kind of internal code. The YouTube is trained from the Conf Island. The YouTube CTC is trained the YouTube Conf Island too. Encoder, decoder, they are most similar, except for CTC, we really don't have much decoder. After we get these 3 teacher model, we apply them to the same YouTube segments. But what we do is we do simple voting. By voting the prediction those 3 teachers. We call the voting method is called ROWER, basically recognize output voting error reduction. That's something we borrow from the previous paper. And the final performance gain is astonishing. So basically, our students can become much better after we introduce the CTC teacher. In fact, in many scenarios, it almost become as good as the teacher model, which is surprising because the teacher is non-streaming, student is streaming, but the streaming student become comparable with the non-streaming teacher. That's something we didn't expect. And if we look at the student WER and the teacher WER, we see that, if we use a single teacher, the student will become much worse. But if we look at the CTC model, the teacher gets some WER like 20%, and the student, in fact, is better than the teacher. And after we combining together all the students, all the three teachers together, the combined student become better, and the result student becomes stronger, and the student is better than teacher. On Spanish, it's 18% reduced to 16%. Our baseline, in fact, was previously 22%. Now you see it's 7% reduction, WER reduction. Similarly, for Portuguese, the teacher is 21.9% WER, and the student WER is close to 20%. Student better than teacher. The same scenario happened in French. In French, in fact, the RNT teacher gets stronger, but the stronger teacher does not lead to the strongest student. In fact, the strongest student is always learned from the CTC. So that means, to summarize, two takeaways. One is, even the CTC teacher is not the strongest, but it can teach very good or very competing student. Second is, to make a strong teacher, we just ensemble RNT and CTC together, and the result students consistently perform well, and sometimes, most of the time, even outperform its teacher. So that's almost the model we launched last year. We launched a number of models using these techniques, and then for cloud, we have a lot of things. But I still want to provide some information for the ablation study. So that means the RNT student trained on CTC teacher outperform their counterparts. And our paradigm is showing that we should use at least one CTC teacher. We should combine CTC teacher and RNT teacher together. And then later, I think recently we have some paper published. We show that we are using not only CTC teacher, but also the we use more than 3 billion parameters to train a big transformer-based model. Using CTC and RNT combined together, even boost the performance in a number of not only cloud metric, but also the pixel form metrics. And if we compare with this work together with our previous the RNT teacher only, and we clearly see the benefit of CTC just boost the performance a lot. And that was surprising to us, because nobody realized the CTC was so powerful until we had our adverse attack, and then adverse attack gave us the motivation, and then we apply this motivation to our framework. It just gets the strongest boost. Okay, and here is our final model. So the previous model is the 20%, 20%, 28%, 25%. Now we reduce them into something below 16, below 10K, and below around 16. And the relative improvement, kind of like the T-Bot was very excited at that time, like relatively reduced the 40% of WER for Spanish, and the 27 for relative reduction for Portuguese, and the 13% for French. Yeah, that almost finished our journey. So to summarize, we first go over with RNT model and the CTC model, and then summarize the background, and then show our team's effort of reducing the long-form error. The lesson I learned is the model upgradation is usually not easy, especially if your model infrastructure compared with the traditional infrastructure are very different. But when those things are not easy, that's probably very good for researchers, because it just creates an interesting problem for researchers to solve. And then if we can solve this, we have a very huge production impact that makes everybody happy. The last one is what I learned from my colleague in Google. So basically, we share the same code base. We just have a lot of collaboration. Sometimes collaboration can be hard, but after we solve the problem, everybody will feel very excited and it's kind of great memory. If we look at each other's the work and contribution or even code change, it's just some experience we cannot forget. That's it. I will I'm happy to explain more if you have any questions or take any questions you want.
Thank you, Dr. Cao. So very informative talk. And any questions from the audience? You can unmute yourself. So actually, I can ask several questions first. So very great work and very interesting. And the first of my question is that, so based on your slide, it looks like for each language, you train one model, right?
Yeah.
Whether it's like any possibility that we have the kind of the very unified model can deal with the different languages for the, that's also it's kind of end-to-end model. Right? We that in NLP we have that so-called multi-language model, but right now since you integrate the audio and the language model together, whether we have such kind of a model that can its input can receive the different types of the language, the audios of the language and the speech, and then it can also deal with at the back end can deal with the different language.
Yeah. And that's sorry. Go ahead, please.
Yeah, that's my first question.
Yeah, that's a very good one. So I think the answer for this question was impossible, almost impossible, was impossible when before end-to-end learning. But after end-to-end learning came to the existence, it's possible because we can, in practice, we can, throw all the data together and then use a multi-language token, the encoder to decoder to generate this. My colleague Tara and Bo in Google Speech already have some papers, and I think they will make more efforts to make that paper into production. But into production means the model, the recipe must be very matured, and then you cannot make mistakes. When some, the mistakes can be some users can speak with accent. You don't misinterpret them and then the generalities. But the final answer is yes. And that's the benefit of the bless comes from the blessing of end-to-end.
Okay, thank you. And another question is that, so you show some of the papers, actually this kind of target kind of on device, right? On device end-to-end. And so from your perspective, so what is the kind of the different requirement for those that the end-to-end model on device and the cloud? So except this kind of the common difference, like the model size and so on, is there any other kind of specific requirements that when we consider deploy a model on device or deploy a model in the cloud?
Yeah, so this is very important. In fact, the different production teams will have defined their different metrics. For on device like Pixel phones, I think the important metrics is when the user finish talking, like I want to say search for some, I want to tell my Pixel phone like search for the location of Rutgers University. I hope the Pixel phone can answer questions right after I finish. It shouldn't wait to say, oh, find the location of Rutgers, and then I wait for 1 to 3 seconds and then tell me that. That kind of interaction will become very unnatural, especially when I speak to the phone. I feel like, oh, my phone probably didn't answer my question. Is he or she listening? That kind of interaction. So those human interaction-based metric will be very important for on-device, but not so significant for cloud, many cloud customers. Of course, cloud customer they diversify, but I mean, I'm talking about one of such difference that because different product, different customer has different requirement, like the on-device customer, Pixel customer will have become more sensitive with the metric I mentioned that should be latency, but cloud is not so critical about latency. Another kind of difference is a big difference is in cloud we can allow bigger model. On device you need to make sure the model can be compressed and then saved into the Pixel phones or Android phone or even the Apple iOS phones, the iPhone. But on device, you need to make sure the model is less than, say, 300 megabytes. And these device related to the metrics are important. In cloud, we don't have such strictly constrained things. That's the second difference. I cannot mention all the differences, but I want to mention the last one, which is in cloud, there are more user cases about long form. On device, such long form testing set are not very important. For example, some cloud customer may have some agent customer conversation, which can be, say, I call AT&T complain. I'm just randomly generate. I call some utility company complaining that my Wi-Fi does not work or other things work. So all those are make-up examples, but you can imagine those in real scenario, such conversation can be as long as a half hour or 20 minutes.
Yeah.
But you don't talk with your Android phones.
Yeah.
So that's why long-form error was more important for cloud. Can be important for Pixel phones, but not so dominant important. So that's why long-form was our team's focus in the past 2 years. But again, those things are changing. We have the different new phones almost every year. New phone will have different memory, different assumptions. Some phones will have TPUs, NPUs. So working with on device is, I would say, is definitely more exciting, more challenging, because basically you are playing with a very small space. So my team, my colleagues did a great work. But on the other hand, cloud customers are diversified. We need to make sure they are happy, and we optimize basically different kinds of metrics for them.
Thank you. And actually, a follow-up question that's related to the metric you mentioned. So we know that for the device scenario, so the metrics about latency, memory, power, subs, and for the cloud, I think it's very important, the metrics about the data privacy. So I remember you also once mentioned that, like, for example, so when you build a model, you cannot touch the customer data, right, for the production. Yeah. So I was wondering, so because in the academia right now we're talking about the encrypt, directly you operate your DNA on the encrypted data and so on. So I was wondering, so is there any the research progress in this direction? Because if it really works, and then I think maybe you can directly train your model on those encrypted custom data.
Yeah. So the trend I saw, we will have a data hungry game everywhere. Everywhere means probably all the companies in the US, not only Google. But in practice, what happen will be now every industry companies are examining their data, their legal agreement with the customer. For example, if the legal terms was not clear, probably they need to delete all the data and then ask the customer to sign again. Just to give you an example like this is, for example, even if we get data from the customer, we need to first redirect to just remove the sensitive information from these. Basically, if customer talk about name, locations, everything, we need to remove them. And then we are not allowed to let human researchers to listen to the audio. So we can run machine jobs, but the machine job cannot write the prediction to the disk, cannot just show all the customer what, cannot allow the, basically some machine job can be run, some machine job if do not have the prediction cannot be run. So all the access need to be monitored or recorded. And even worse, you know, good or bad, good for the customer is when we have the customer, when the customer leave Google, for example, we need to delete the data in 15 days or 2 weeks. And even before this, after this, all the feature, when we extract feature from its customer data on the disk need to be removed. So we have some cron job just running almost every week. So basically delete the data 1 week ago and then regenerate it again. Why? Because you don't know whether the customer has left or not. So every time you need to regenerate and then make sure the new data will be automatically deleted after two weeks. So all these efforts are a lot very good from the customer protection point of view, but create so many bugs and troubles for us. Sometimes I joke with with our team saying that, oh, if we allow to read or listen to the customer data, we probably can solve this problem in 1 day. But in fact, we cannot. So we are doing all kinds of machine learning and try all kinds of guessing. Maybe take us 1 month or 2 months to solve or guess the answer to solve the problem. I think I haven't answered your question, what will the future will be, but I clearly see the trend data will become more and more difficult in the future. Of course, technology like federated learning or other things can if the preserve the computing can alleviate the problem, but there will be a long way for us to build a very matured data paradigm in the future. And yeah, and a lot of problems are not, we cannot imagine what the problem be until we really were hit by the problem.
Thank you. Any questions from the audience? I think I asked a lot. So if no more questions for audience, actually I would like to ask some additional ones. And you just mentioned about the federal learning. So how do you think about like the federal learning in the speech domain?
Yeah, federated learning will be more and more important for on-device, right? Because whenever we receive some data on server, there will be the kind of data issue. The user will be concerned that the data will be used. But all the federated learning came at a cost. Like basically your device is keep computing. And like the energy is consumed, and the on-device is smaller than server. So basically we pay the price. And the most importantly is federated learning. I mean, we all researchers, right? So like we know sometimes the machine learning model don't work. And the federated learning cannot guarantee prevent these worst scenarios. Well, maybe we have some, kind of protection at the worst scenario, but you cannot always guarantee that the model may become worse or become better. Hopefully become better, but because you don't have researcher monitoring that, you don't know. So I guess it's kind of trade-off between whether you want a stronger model or what kind of data protection you want to be following. I'm kind of optimistic that in the future there might be very there are a lot of rooms, especially for researchers from academia, a lot of rooms to try new models. But I also see there are a lot of price we need to pay for production to use federal learning in real on device, especially in large scale. Sometimes it may also hurt the user experience. So user experience vs the privacy. The industry need to be very careful to balance the two. The ideal will be we have very good user experience and also very good data protection. That's a long way to go. Yeah, but I hope academia researchers can provide a more solution and even in the sense that I'm a little worried that my knowledge will be outdated in 5 years, but also I will be excited if you have such smart algorithms.
Thank you very much. Okay, so if no more questions from the audience, so let's thank our speaker again. So thank you, Liangliang. So I really learned a lot from your talk. Very
thank you. Okay.
And also thank everyone for attending our this week seminar talk, and see you next week. Thank you. Have a wonderful day.
Thank you. Thank you for me. Bye-bye.
Bye.